Hi, in this video, we're going to take a look at regularization techniques in logistic regression. Okay, so the idea here is I want to avoid overfitting on my logistic regression model. And to prevent myself from overfitting, to protect myself from overfitting, what I'm going to do is instead of removing predictor variables manually, like we could do with forward selection, backwards elimination, forward back. What we're going to do instead is that we're going to mute down and shrink the coefficients in my model. And so this way, if a predictor variable should have been like kicked out, it's going to have a small coefficient, and it really won't be that big of a deal that we left it in. And so this is a pretty good way to go about it. Now we're going to go over 3 different techniques. We're going to go over lasso, ridge, and elastic net. Elastic net is a combination of the two. Lasso, you can think of this as like degree 1 or absolute value on the coefficients. And then ridge is going to be taking the absolute value squared. So it's going to be like related to the L2 norm. All right, now, lasso and ridge will have, we honestly will ultimately get like similar models, but there will be a difference. Lasso, it'll actually shrink down predictor variables down to a coefficient of 0, which we interpret as the predictor variable is getting kicked out of the model, so it's done feature selection for us. Now, ridge regression, practically, from a theory point of view, it will never shrink a predictor variable's coefficient down to 0. Now, up to rounding off, up to machine accuracy, it could operationally be 0. But from a theory point of view, it's going to shrink it down. All right, so Lasso will do feature selection for us, which is great. Now, ridge regression is not going to kick anything out. And so I've encountered people say, well, you don't want to use ridge because it won't kick things out. Hold up. Ridge is an excellent choice when you're in the situation where you have to include predictor variables that are collinear with each other. You have to include predictor variables that are just noise. If I have junk predictor variables I have to keep in because of my stakeholders, or I have collinear predictors where I know it'll be problematic if I kept all of them in there, ridge regression will shrink them down. Now, when would we be in the situation like this? Well, think about if your stakeholders just say, we must have this predictor variable in there. Another situation, and I've had this experience with my human resources work, is that legally I have to keep predictor variables in there. Right, so imagine I'm in a situation where we're using an established academic paper to justify what we're doing with our model. And so this way we say, if I get legal scrutiny under what happens, I can go, hey, this academic paper over here, which is the gold standard, use exactly these predictor variables. I use these predictor variables also, so you can't critique my model from a legal point of view. And so we're in a better situation. And that's something that I've had to deal with for human resources in particular. And so what that had done, what happened with those models is that when I had a junk predictor variable or a collinear predictor variable in there, the coefficient shrank down and I was protected from overfitting. Now, something to consider with this is that it's better to not have junk predictors in there if you can. Garbage in, garbage out. If I put in junk predictor variables into my model, the algorithm isn't going to overcome it. Honestly, it's better to put in quality ingredients into the cake than to try and have a master baker, take poor ingredients and improve it. Do not lean on these techniques to skip over your feature selection. It's more important that we do thoughtful, careful model building in the first place. We need to put supervised, adult supervision into our supervised learning models. We can't just say, hey, Lasso picked it, I'm done with it. No, garbage in, garbage out. Remember that there will be fluctuations in our data that are not consistent with the true population. And those fluctuations, maybe Lasso would think that it's a good predictor variable when it's not. Maybe Ridge will think it's a good predictor variable when it's not. We always need to use our feature selection, our adult supervision of the modeling process, instead of just dumping into an algorithm and hoping for the best. Garbage in, garbage out. Ridge, Elastic Net, and Lasso will improve the situation, but it's better to put quality ingredients in from the beginning. All right, so our first regularization is Lasso, also called L1 regularization. So here, we're using the L1 norm in on this on our coefficients. And here is a penalty term. So what we're going to do is we're going to evaluate the fit of our model. So the quality of the fit that I get along with a penalty term to counteract like how complicated of a model I have. If I have big coefficients, you can see that this penalty parameter is going to, the penalty parameter times the sum of the absolute value of the coefficients will be a bigger aspect to it. Now, something about this type of modeling also is that it's super important that we do rescaling of our model before we start fitting. Many of the functions in R will automatically do the rescaling for us, but honestly, I don't trust it when I'm actually using this for work. I go through and I rescale beforehand. Now, Ridge, here I'm squaring the coefficients, then adding them up. All right, so this is the 2 norms squared on the coefficients. And here I've got my penalty parameter. And so what I'm doing is I evaluate the fit, and then I take, like the mean squared error, and then I tack on that penalty aspect to evaluate, do I have a good model or not? And then Elastic Net combines, takes the L1 norm of the coefficients, the L2 norm squared of the coefficients, takes a weighted average of the two, alpha is between 0 and 1, and then applies the penalty parameter. So it's always, always, always 100% important that I have my predictor variables on the same scale. Now, if my data comes to me and everything's between 0 and 10, or between 0 and 1, 1 to 100, something like that, I usually don't need to rescale it. But if I have different scales, like let's say I have height and weight in my data frame that I need to rescale. If I have 2 columns on different scales across the entire data set, I need to rescale the whole thing. I was talking to a student last night who was resistant to rescaling his data when he was doing k-means clustering. He had like 10 columns all on the same scale, and then one was on a different scale. 1 out of 11 on a different scale. You know what? You got to rescale the whole thing. So rescale it. It's important. Now, if you're limiting the range, or you're subtracting the mean divided by the standard deviation, that's not as important as that you just do it. My opinion is that for most spreadsheet problems, at least the problems I tackle, usually we want to subtract the mean divided by the standard deviation. That works out pretty well. Also, there's more of a linear regression theory point of view, and logistic regression also, for that type of transform, instead of changing the maximum and minimum range. But do what works for your project. Now, for the optimal parameter for the penalty aspect, or with that alpha, we'll use like cross validation. We'll use other techniques for parameter tuning. And many of the functions like glmnet will actually go through and find it for you. But typically we use like cross validation to find what's the best value. And regularization will prevent overfitting and protect us from multicollinearity. Now, what will happen typically when I have multicollinear predictor variables, and those predictor variables are informative. So let's say I have like height, I have shoe size, and I have hat size. And and somehow a person's size is related to the target variable. Those are all going to be collinear with each other. And what assuming that that person's size is connected to the target variable, what will happen is it's useful. So Lasso is not going to kick those out unless it really needs to. It's going to keep all 3, but it's going to shrink the coefficients down to make sure that none of them are overfitting with each other, that it really doesn't have much of an impact on that. And so that it'll work out pretty well for us. Informative multicollinear predictor variables will be kept, but though the coefficients are shrunk down so that we don't really have a problem with overfitting. All right, so Lasso tends to exclude predictor variables by assigning 0 coefficients. So this is a useful way to do feature selection for us. So I can run, so if I'm going through the process and I've got like 1,000 predictor variables, it's too many for me to wade through. I can't figure out what's good, what's bad manually. Lasso is a good way to like narrow it down, like start kicking some stuff out. Ridge will rarely squeeze things down to zero. Usually if it's squeezing it down to zero, from a theory point of view, it's not actually zero, it's just zero up to rounding inside the computer. And so this is very useful if I have to keep predictor variables in there. For example, if my model could be following under legal scrutiny, and I need to be able to defend why what the model I picked. And so I can say, hey, this paper over here used these predictor variables. I use these predictor variables. This gives a lawyer one less route to scrutinize my work. And also, I've had this happen multiple times, is that my stakeholders demand that certain predictor variables have to be in there. I've looked at them, I've got, right, I've got problems with collinearity, or darn it, these are junk predictor variables. What do I do? Ridge keeps them in there. Also, Elastic Net will keep them in there because that's a linear combination of the two, of Lasso and Ridge. All right, so let's just run through different packages and take a look. So first I'm going to load my data. And so once again, I'm going to use the SA Hart dataset from Elementary Statistics Learn. Just do a little bit of light data prep of converting family history to dummy variables. And the first one I want to talk about is glmnet. So glmnet implements Lasso, Ridge, and Elastic Net for generalized linear models. It's, from my internet search, my exposure at work, this is by far the most common package for regularization. It's efficient for large data sets. It handles Lasso, Ridge, and Elastic Net. It can handle like sparse input matrices. It does coordinate descent algorithms for optimization. And my experience is it's the best one to work with. There are other ones. There are some excellent packages out there. I just prefer this one. Now, the big difference here compared to other setups, like if I'm using regular old GLM, is that you notice that I don't have a formula set up here. So I've got my predictor here. So here I've got my predictor variable. So notice I'm getting rid of the target variable. I'm rescaling. Now here is kind of a problem that I've had in the past, is that glmnet requires it to be a matrix for your predictor variables. I had a problem with this. I couldn't figure it out for a while. Eventually I got it. I read the help documentation. Now here, y needs to be a vector for the target variable. And for a binomial target, it needs to be a factor. And so boom, I've got that. And here, family is equal to binomial. I've never ran it with a different length function, by the way. I assume it would work, but I honestly don't know. All right, now the cross-validation function in glmnet will go ahead and figure out the optimal or approximate the optimal parameters for us. And so what it's going to do, it's going to find the minimum for us on that our loss function plus the penalty. And so here's that lambda. Now, what it's going to do, it's going to look and it's going to see, hey, you know what? I don't really need, if I was to just, increase that penalty parameter a little bit within like one standard error away, then I'll get, I'll get a simpler model. I'll shrink it down more. And so then boom, I can get that down. And so here, one standard error. So operationally, you can see that these are going to be pretty much performing pretty close to each other. But here I have a larger penalty parameter. And with that larger penalty parameter, I'm going to have a simpler model. And so I'm less prone to overfitting, but I haven't really exposed myself to a loss in model performance. And so here I can specify the lambda. I went ahead and went with 0.05. It's a little bit bigger than here. And here are the predicted values. And also in here, I didn't do it, but I can specify what is the alpha value, which will I can't remember for this either. I think the default is Lasso by not specifying. If I put in a parameter, the alpha equal to 0, it'll be Lasso or Ridge. 1 will be Lasso or Ridge, and anything in the middle will be Elastic Net in between. And so here I'm just doing the prediction, and I'm going to go ahead and compare the models at the end of the video. Now, caret also will implement Lasso and Ridge in several different ways. And so how caret works is that the training function invokes other packages for us and functions from those packages. And so this is an easy way for us to be able to go through multiple model structures with relatively low work. So one of the huge disadvantages of R for supervised learning is that if I want to use this package or this package or this package, I have to learn something different. I have to go through the process. This one uses formulas. This one uses X's and Y's. This uses X's and Y's. X must be a matrix. It can't be a data frame. This one over here has another weird format. And every time I build a new model, I have to go through and kind of learn the individual package all over again. Caret streamlines this with nearly one consistent presentation. It's a huge improvement. So one thing that is a huge advantage of sklearn over R is that we have a consistent presentation for how we interact with the models. I badmouth Python a lot, but this aspect is much better. It's so much nicer to be able to get through functions relatively easily. All right, yeah, so caret interacts a lot of other packages, including glmnet. And so we've got extensive functions for data splitting, pre-processing, feature selection. It really is a one-stop shop for supervised learning. And it's pretty easy to compare different models, and it's easy to implement different models. I feel like caret is one of the best approaches for comprehensive model training and tuning when various machine learning algorithms need to be considered. And so here, with the train function within caret, the big thing that's different from what I had before, here's my X, here's my Y, just like I had, I just specified glmnet. And now when I get my predicted value, it's a little bit different format because I've got caret on top of glmnet. When I make this prediction call, I'm not making a call on glmnet. I'm making a call on the caret train function, the object from caret, and then then caret goes in, identifies the class of the model, and then works through the process of getting the actual predictions. And so there's a couple layers in there. Here I'm extracting the model probabilities. Up here you'll notice I'm getting the response. It's going to end up being the same thing or the same output ultimately if I had exactly the same models being produced. Now Penalized is another package for Lasso and Ridge. It focuses on penalized maximum likelihood estimate for logistic regression and other models. And we can do penalized and unpenalized predictor variables. So we've got Lasso and Ridge and combination of the two. This is designed for high dimensional data and provides a penalized model fitting with automatic selection of that penalty parameter, which is very nice. So just like we saw before with that CV function. And this is best for logistic regression where other models where penalized maximum likelihood estimation is crucial, especially in high dimensional settings. And so here I'm using the penalized package. I'm using the optimization of L1 on this. And, so we can just see here is the response. Here is the, the penalized version. So here I specify which ones are penalized and which ones are not on this. And I'm saying it's a logistic regression. And I specify the minimum and maximum range for the lambda values. And here I'm going through the process and just fitting this through. And I go through, and to do the predictions, I just use the predict function. Now with this one, I actually have to use penalized predict. So it's not technically a proper method in R, but it's okay. It would have worked if I would have loaded the penalized package using library. Now Ridge specializes in ridge regression. I know your shots. It's amazing. So here, it's dedicated to ridge regression analysis, has the option to rescale predictors by the correlation matrix. So here, instead of rescaling the individual columns, we're rescaling it by the correlation to help untangle, correlation in there. Now, this has, from a theory point of view, a very nice aspect to it because that resolves that problem for us. I tend to not use that because it just, I've just got more experience with regular columns, normalization, but definitely a powerful tool to have in our tool belt. And we can use principal component to estimate the penalty parameter. Very nice. It's simple to implement, and it does not perform variable selection. So this is nice if I have to include predictor variables in my model. Now, we could use Ridge for feature selection by just eliminating the lowest coefficients. The predictors have the lowest coefficient, kick them out, and then retrain the model. Kick it out, retrain the model, and that would be a way to use Ridge for feature selection. And this is good for pure ridge regression scenarios, particularly when all predictors are to be retained in the model. And so here, the function is logistic ridge in the ridge package. Here's that formula that I've been using so far. My data, I'm rescaling by the correlation, and my lambda is going to be decided by the function is going to go through and do a PCA for me. Underneath the hood, I'm not even going to look at it. And then to get the model probabilities, I'm going to use a predict function, and I'm going to get the response off of it. All right, so now let's go ahead and actually compare those predictions. And so what I'm going to do, I'm going to go through, and if the model probability was greater than a half, I'm going to say, hey, I'm going to mark it as a 1 for chronic heart disease, or I'll mark it as heart disease. If it's less than or equal to a half, I say no heart disease. And I'm going to go through all my different models. I'm going to go through and I'm going to check to see the performance of what's going on. And so I'm going to do a contingency table, and then I'm going to get the confusion matrix. So here is the glmnet. Here is my accuracy. And we're going to see our sensitivity, specificity, prevalence, detection rates, balanced accuracy. And so, we can dig into it. I'm going to just focus on accuracy because it's simple to understand, even though, when I have, an imbalance here, which I definitely do, it's a little bit easier to figure out. Now for caret, so here we have 0.742. Here's our sensitivity specificity, about 0.4, 0.9. And here we have about the same accuracy, about 0.5 and 0.9. So here we're doing a little bit better with caret. Now here we have penalized. And so here we've lost a little bit of specificity, about the same accuracy. And you'll notice that these are relatively close to each other. There isn't a whole lot of difference in the performance aspect. All right, so for your homework, what I want you to do, I want you to take your data, take the data that you're interested in, and run logistic regression with Lasso and Ridge. And if you want, go ahead and do Elastic Net. Enjoy it. Explore the model, see what different lambdas do, and post it on WebCourses Canvas. All right, that's all I've got for you. Life is short. Do math.